design a RC beam. So the question is, design a rectangular simply supported RC beam over a clear span of 6 meters. So here the span of the beam is given. So what is the clear span of the beam? It is 6 meters. If the superimposed load is 12 kilonewton per meter. So the imposed load or the live load which is acting on the beam is how much? It is 12 kilonewton per meter. And the support width is 230 mm for the simply supported beam. And the materials used here are given as the grade of concrete as M20 and the grade of steel as Fe415. And the width of the beam is given as 300 mm. Here he is asking us to design the shear reinforcement. So for designing the shear reinforcement, first what we have to know? We have to know the design shear force. Is it or not? So here in this particular question, the depth of the beam, that is the effective depth of the beam, is not given. First let us write down the given data. So what all are given here? Here the clear span of the beam is given, which is 6 meters, and imposed load is given. The imposed load is being 12 kilonewton per meter. Support width is given. The support width being 230 mm. The grade of concrete is given, which is 20 Newton per mm square, and the grade of steel is given, which is 415 Newton per mm square, and the breadth of the beam is given, which is 300 mm. So here what? The effective depth of the beam D is not given. Reinforcement details are not given here. Whether this beam is singly reinforced beam or is it a doubly reinforced beam, those details are not given. The factored moment, the factored shear force. So all these things are not given in this particular question. So first what we have to do, we have to design the beam. So design the beam in the sense you have to find out the depth of the beam. What will be the effective depth of the beam? What is going to be the overall depth of the beam? We have to calculate the factored moment, factored shear force. We have to calculate the limiting moment of resistance. We have to know whether if it is a singly reinforced beam or a doubly reinforced beam. We have to calculate the area of steel. If it is a singly reinforced beam, we'll find out the tensile steel area. If it is a doubly reinforced beam, we will calculate both the tensile steel area as well as the compression steel area. And then later we have to design for the shear reinforcement. So here in this particular column, we have to design the complete beam right from the starting. So the design of RCC beam, if we have already discussed in the previous chapter, that is in the second chapter, we have already seen how to design a singly reinforced beam, a doubly reinforced beam, and a T-beam sections. So we will apply the same concept here in this, and later on, after designing a beam, RC beam, having all the dimensions, that is the breadth, the overall depth, the effective depth, the area of steel, the moment, everything, then we will design for the shear reinforcement. So first let us design an RC beam. So what are the unknown parameters here? The unknown things is we have known the beam. So first what we will do is, in the step 1, let us find out the effective depth for the particular beam. So the step One is to calculate the effective depth D. Here what? I'm going to calculate the effective depth D. So how we have to calculate the effective depth D? So in clause 23.2.1a of IS 456 2000, the ratios of L by D, that is the clear span by effective depth ratios, are given for different beams, that is for different types of supports. If it is a simply supported beam, the L by D ratio is given. For cantilever beams and for continuous beams up to a span of 10 meters. So if the span is 10 meters and below, then the L by D ratios for different supporting systems are given in this particular clause. So here I am taking, as it is a simply supported beam, mentioned a simply supported RC beam. So the L by D ratio is mentioned in this 23.2.1a, and the L by D ratio can be taken up to 20. That is, the L by D ratio can be taken up to a value of 20. So here what I am doing is, I am considering the L by D ratio as 15. I am considering the L by D ratio as 15. So from this what I can get? I can get the value of D as L by 15. So the effective depth D will be equal to L. L is nothing but the clear span. So 6 meters. So 6000 divided by 15 will give me the effective depth D, which is 400 mm. So the effective depth D is 400 mm. You can assume any other ratios also. L by D you can take 20, you can take 10 also can be taken. So up to 20 the L by D ratios can be taken. But mostly in most effective cases is L by D ratio, the range you can take from 12 to 15, so that you will get good values. So the range for stiffness if you want to consider. So the range L by D can be in between 12 to 15. So I have considered the 15 and from that I have calculated the effective depth D as 400 mm. Now let us find out the overall depth. So the overall depth D is what? The effective depth plus the effective cover. So here what? I am assuming an effective cover of 50 mm. So assume effective cover as 50 mm. So then what will be my overall depth? My overall depth D will be 400 plus 50 mm, which is 450 mm. So the first step what? I have calculated the effective depth D 400 mm, and from that I have calculated the overall depth capital D, which is 450 mm. Now in the next step we will calculate the effective span. So in the question here he has mentioned the clear span, but while designing we will consider the effective span of the beam. So as the clear span is given here, now let us find out the effective span of the beam. Now the next step is to calculate the effective span of the beam. So in the next step we will calculate the effective span. So how we have to calculate the effective span? So to calculate the effective span, check clause 22.2a of IS 456-2000. So in clause 22.2a of IS 456-2000, the formulas for calculating the effective span of a beam are given. So what it is given is the effective span can be taken as center to centered span and the other one is effective. The effective span is taken as one is the center to center of supports and clear span plus D, whichever is less. Out of these two, whichever you will get the less value, that value has to be considered as the effective span of the beam. So first let us find out the center to center of support distance. So how will calculate the center to center of support distance? It will be clear span plus the support width. So here what he has given, that is the support width is given as 230 mm. So what a simply supported beam will be supported on both the ends, isn't it or not? On both the ends. So here what you have to consider, you have to consider the center to center of the supports. So center to center of the supports is what? Support width divided by 2, that is one support half, plus the other side half also you have to consider, plus the support width divided by 2. So this will be, what is the clear span? It is 6 plus what is the support width? 230 mm. That one I am converting it into meters. So 0.23 divided by 2 plus 0.23 divided by 2, which will give you a value of 6.23 meters. So what is the effective span when I am considering the center to center of supports? It is 6.23 meters. Now let us consider the second case, that is what? Clear span plus the D. D here is nothing but the effective depth. So let us find out the effective span considering this condition. Now, so what is the value I have got here? It is 6.23 meters. Now the second condition, it is clear span plus D. So what is the clear span? It is 6 plus D is nothing but the effective depth. So here I am writing it in meters. So it will be 6.4 meters. So out of these two, which one you have to consider as the effective span? The least one. Out of these two, which one is less? That has to be considered as the effective span of the beam. So here 6.23 meters is the least value. So the effective span of the beam is how much? It is 6.23 meters. It is 6.23 meters. Now we have have calculated the effective span. So the next step, we have to calculate the factored bending moment and the factored shear force. So the next step is what? In the step 3, we have to calculate the factored bending moment and the factored shear force. So what is the formula for the factored bending moment? Here what is the load it is given? It is 12 kilonewton per meter. So the factored bending moment can be calculated by W L square by 8. But here W here is what? W is nothing but the factored load. That is the factored total load has to be calculated first. So how will calculate the total load? So the total load is the sum of the self weight of the beam plus the live load or the imposed load which is acting on the beam. So the imposed load is already given in the question. It is 12 kilonewton per meter. But the self weight is not given. So first what we have to do, we have to calculate the self weight of the beam. So let us calculate the self weight of the beam. So we will calculate the self weight of the beam. B into D into the unit weight of RCC. So B is here nothing but the breadth of the beam. So breadth of the beam is already given in the question, which is 300 mm. So that is 0.30 into depth, that is the overall depth of the beam, which is 0.45 into the unit weight of RCC, which is 25 Newton per meter cube. So if you solve this, you will get a value of 3.375 kilonewton per meter. So the breadth of the beam, the depth of the beam and the unit weight of RCC, which is 25 kilonewton per meter cube. So from this, the self weight of the beam, you can get it as 3.375 kilonewton per meter. And what is the superimposed load? The imposed load is given as how much? 12 kilonewton per meter. So these are the two loads. So from this, what we can find out? We can find out the total load. So the total load will be self weight of the beam, which is 3.375 plus the imposed load, which is 12 kilonewton per meter. So from this, you will get a total load of 15.375 kilonewton per meter. So this will be your total load. So while designing, in the previous sessions already we have discussed, while designing what you have to consider the factored load. That is, you have to multiply the load with a suitable partial safety factor. So based on the load combination. So what are the load combinations we have here? One is the self weight of the beam, that is the dead load, and the other one is the live load or the imposed load. So if both these are acting on the beam, then what will be the factor, partial safety factor? The partial safety factor is 1.5. So the factored load will be 1.5 into 15.375. So from this you will get a value of 23.06 kilonewton per meter. So this will be your factored load, which is 23.06 kilonewton per meter. So from this factored load, you have to consider this factored load and calculate the factored bending moment. So now let us calculate the factored bending moment. Now let us calculate the factored bending moment. So the factored bending moment mu is equal to WL square by 8. So what is W? W here is nothing but the factored load. So what is the factored load we got? 23.06 into L. So what is L there? L is nothing but the effective span, which is 6.23 whole square divided by 8 will give you the factored bending moment. So if you will calculate this, you will get a value of 111.87 kilonewton meter. So this is what the factored bending moment mu value you are going to get, which is 111.87 kilonewton meter. Now let us find out the factored shear force. The factored shear force BU can be calculated. So the maximum bending moment, it is WL square by 8. Then what will be the shear force? It will be WL by 2, which I have already studied previously. It is WL by 2. So what is W here? W is 23.06 into L. L here is nothing but the effective span, which is 6.23 divided by 2. If you solve this, you will get a value BU as 71.83 kilonewton. So this is your factored bending moment mu, which is 111.87 kilonewton meter, and the factored shear force BU, which is 71.83 kilonewton. Now we have found out the bending moment and the shear force. So now what? We have known the breadth of the beam, the depth of the beam is known, the effective span is known, the bending moment is known, and the shear force is known. So, and what are the unknown things here? One thing is we have to calculate the area of steel, that is the longitudinal reinforcement. The main reinforcement is what we have to calculate, and we have to know whether this beam is a singly reinforced beam or a doubly reinforced beam. Okay, and we have to calculate if it is a singly reinforced beam, the area of steel in the tension phase has to be calculated. If it is a doubly reinforced beam, the area of steel in the tensile as well as the compression has to be calculated. And then we have to go for the design of the shear reinforcement. So the next step, that is the step 4, is to calculate whether, or is to know whether the depth what we have assumed here, D, is it adequate or not, and is the section a singly reinforced section or a doubly reinforced section. That is, we are going to find out whether the depth, that is the effective depth what we have assumed, is it adequate, and we are going to find out the mu limit value to know the beam if it is a singly reinforced or a doubly reinforced. Now let us calculate the required depth for the factored bending moment, that is the required effective depth D for carrying the bending moment mu. So the step 4 is to calculate the required effective depth for carrying the bending moment mu. So how we will calculate it? We have already discussed this. Mu is equal to 0.36 FCK B into XU limit. That is, here we are calculating the balanced depth. So XU limit into D minus 0.42 into XU limit. So mu, we have already previously calculated the mu. Substitute the value of mu here. So what is the value of mu we have got previously? Mu is equal to 311.87 8 kilonewton meter. So 311.8 into 10 to the power of 6 is equal to 0.36 into FCK. FCK is the grade of the concrete, which is 20, into B. B is the breadth, which is 300, into XU limit. So XU limit, what is the grade of steel here? It is 415. So it is 0.48 into D. So D minus 0.42 into 0.48 into D. So from this we can calculate the value of. So from this we can calculate the value of D. So if you calculate, you will get a value of D as 367.62 mm. So the required effective depth for carrying this particular moment mu is 367.62 mm, which is less than the assumed depth. So the assumed depth is how much? It is 400 mm. So the effective depth what we have assumed is adequate. So the assumed depth is adequate. So what we have assumed is adequate because the value, the depth what we have got, it is less than the assumed depth. So it is adequate. So we can use this depth D as 400 mm and we can go for the further design. So now what we have calculated the depth. Now let us calculate the limiting moment of resistance so that we can compare both the MU and MU limit to know what type of beam it is, whether it is a singly reinforced beam or it is a doubly reinforced beam. So let us calculate the limiting moment of resistance. So now let us calculate the MU limit, that is the limiting moment. So MU limit is equal to same 0.36 FCK B into XU limit into D minus 0.42 XU limit is equal to 0.36 into FCK is 20 into B. How much is B? It is 300 into 0.48 into D. D is how much? 400 into 400 minus 0.42 into 0.48 into 400. So if you solve this, you will get a value of MU limit as 132.4 kilonewton meter. So this is going to be our MU limit value, that is 132.4 kilonewton meter. Now what we have to do, we have to compare MU and MU limit. So if you compare MU and MU limit, what you can observe here, that is MU is less than MU limit. So if MU is less than the limiting moment of resistance, then what you have to design for a singly reinforced beam. What? You have to design for a singly reinforced beam. So now we have known the values of MU and MU limit. Now what we have known that it is a singly reinforced beam section. So in a singly reinforced beam section, what you have to provide the steel reinforcement only in the tensile zone. So the next step, that is the step 5, is to calculate the area of steel which you have to provide. That is, we have to calculate the AST. So now let us calculate the area of tensile steel to be provided. So now the step 5 is to calculate the area of tensile steel or the tensile reinforcement. So how we will calculate? By using the formula mu is equal to 0.87 Fy into AST into D minus 0.42 XU. So in place of XU, what you have to substitute? XU is equal to 0.87 Fy into AST by 0.36 FCK into P. You have to substitute XU here in this particular XU. This equation has to be substituted here. And then mu is equal to 0.87 into Fy into AST into D minus 0.42 into 0.87 into Fy into AST divided by 0.36 FCK into B. You know all the values. You know the value of Fy. D is already calculated, which we got 400 mm. FCK is already known, which is 20 Newton per mm square, and B is also known, which is 300 mm. Substitute all the values here. So mu, we have already calculated the value of mu also, which is 118.8 into 10 to the power of 6 is equal to 0.87 into Fy is 415 and AST is what we have to calculate into D is 400 minus 0.42 into 0.87 into Fy is 415 into AST divided by 0.36 into 20 into 300. So, if you solve this particular equation, you will get a value of AST. So, by solving this particular equation, we will get the value of AST as 921.4 mm square. Now, this is the area of steel what it is required for carrying the particular moment mu, that is 921.4 mm square. Now what? Let us adopt or assume the dia of bar is 20 mm. So I am assuming I am providing the diameter of the longitudinal bar is 20 mm. So from this I am going to find out the number of bars. So n into pi d square, 20 whole square divided by 4 will be equal to the area of steel which is required. So what is this area of steel? This is the required area of steel, which is 921.4 mm square. So from this you can calculate the value of n, which you will get it as 2.93. As we cannot provide 2.93 number of bars, I am approximating it to 3 number of bars. So how many number of bars I am providing here? I am going to provide 3 number of bars. That is, provide 3 bars of 20 mm diameter. I am going to provide 3 bars of 20 mm diameter. So let us find out the area of steel which is provided. Now let us calculate the area of steel which is provided. So AST provided. So how many number of bars we have provided? 3 bars, and the dia of each bar is 20. It will give you 942.5 mm square. So the AST what we have provided is how much? It is 942.5 mm square. So what you have to do? You have to check for the minimum and the maximum tension reinforcement. So after checking for the minimum and maximum tension reinforcement, now what we have designed the beam? We have known we have found out the effective depth. We have calculated the effective span of the beam, the moment, bending moment, and the shear force, and we have also calculated the area of steel, the number of bars to be provided, and the dia of the each bar. Now what? In the question is asking to design for the shear reinforcement. Now in the next step, let us design for the shear reinforcement. So the next step is to design for shear reinforcement. So in the design of the shear reinforcement, what is the step? First step what we have to do? Thing is we have to calculate the nominal shear stress, that is tau v. So how we can calculate tau v? Tau v can be calculated by the formula VU by dd. So what is VU here? The VU we have calculated, it is 71.83 kilonewton, that is 71.83 into 10 to the power of 3 newtons, divided by B. What is the breadth here? It is 300 into depth. Depth is 400. So from this, we will get a value of tau v as 0.598 Newton per mm square. So this is the value of tau v is what you are going to get. So after calculating tau v, what is the next thing what we have to do? We have to calculate the shear strength of concrete. That is, we have to calculate the tau c value. So how we will calculate the tau c value? From the table 19 of IS 456-2000. So before calculating the tau c value, we have to calculate the percentage of steel. So what is the formula for calculating the percentage of steel? It is AST by BD into 100. So AST we have already calculated. It is what? 942.5 mm square divided by B. B is how much it is? 300 into D is how much? 400 into 100. So from this you will get the percentage of steel. So if you calculate this, you will get a value of 0.785. So corresponding to this value of 0.785 and the grade of concrete. The grade of concrete is what? 20 Newton per mm square. From the table 19 of IS 456-2000, you have to see the value of tau c. So if you do so, you will get a value of tau c as 0.57 Newton per mm square. If this particular value is not available, you have to take the before value and the after value, and you have to go for the interpolation. So from that, you are going to get a value of the shear strength of the concrete as tau c as 0.57 Newton per mm square. Now we have known the tau v and tau c value. So what is the next thing we have to do? We have to calculate the tau c max value, and we have to compare the tau v, tau c and tau c max value. Now let us calculate the tau c max value, that is the maximum shear stress of concrete. So this can be calculated from table 20 of IS 456 2000. So for the grade of concrete 20 Newton per mm square. Okay, the tau C max value table 20 is given as 2.8 Newton per mm square. Now what? We have to compare the tau B, tau C and tau C max value. So from this values what you can observe? You can observe that tau B is greater than tau C and tau B is less than tau C max. If tau B is greater than tau C and tau B is less than tau C max, what we have to do? We have to design for the shear reinforcement. So what we have to do here? We have to design for the shear reinforcement. So to resist a shear force of VUS. So what you have to design the shear reinforcement for resisting a shear force of VUS. So in the next step what we have to do? We have to calculate the VUS value. Now we have to calculate the shear force which has to be resisted by the shear reinforcement. So next we will calculate the shear force which has to be resisted by shear reinforcement. That is what we have to calculate here. We have to calculate the VUS. So what is the formula for calculating VUS? VUS is equal to VU minus tau C into BD. So VU value we have already calculated. It is what? 71.83 into 10 to the power of 3 minus tau C. Tau C value is how much it is? 0.57 into B. What is the value of B? It is 300 mm into D. What is D? It is 400 mm. So if you solve this, you will get a value of VUS as 3430 newtons. So the shear force which has to be resisted by the shear reinforcement is how much? It is 3430 newtons. So we have known the shear force. So now next what we have to do? We have to calculate the area of the stirrups which has to be provided. So here I am providing the vertical stirrups. So now let us calculate the area of the vertical stirrups which has to be provided. So the area of the vertical stirrups ASV. So here what I am adopting, let us assume I am providing two-legged stirrup and the dia of the stirrup be 8 mm. 8 mm diameter stirrups I am using here, and the stirrups are two-legged stirrups. So from this I can calculate the value of AC as 2 into pi d square by 4. D is here how much? 8 whole square divided by 4. So which will give you a value of ASV which is 100.5 mm square. So this is the area of the vertical stirrups what I am providing, that is 100.5 mm square. So after finding out the area of the vertical stirrups, next what we have to calculate for the shear force which has to be carried by the shear reinforcement. We have to calculate the spacing. So spacing we have to calculate, and the least of all the spacings has to be taken into consideration. So now let us calculate the spacing. That is, let us calculate the SV. So we will calculate the SV. Here we are considering the vertical stirrups. So VUS is equal to 0.87 FY into B divided by SV. So SV will be equal to 0.87 into Fy into B divided by VUS. So we already know the value of VUS which we have calculated now. So what is the value of VUS? VUS is 3430 newtons. So it is 3430 newtons. We know the value of B which is 300 mm and Fy. Fy is nothing but the grade of the stirrups what I am providing here. For suppose let me provide the grade of stirrups as FE415. FE415 grade stirrups I am providing here. So in place of Fy I am going to substitute 415. So substitute all the values, you will get the value of SV. So what here? So I have to substitute all the values here. So VUS is what we have calculated now, that is 3430 newtons, and B is nothing but the breadth of the beam which is 300 mm, and Fy is nothing but the grade of the steel what I am going to provide for the stirrup. For suppose here I am providing the grade of steel of the stirrups as Fe250. So in place of Fy what I have to substitute? I have to substitute the value of 250. So substitute all the values here, that is 0.87 into Fy is 250 into B is 300 divided by VUS is 3430. So from this you will get the value of SV. The value of SV you will get is 2549.1 mm. So the value of SV is how much? 2549.1 mm. So next we will find out the minimum spacing from minimum shear reinforcement. Now let us calculate the spacing. So how we will calculate the spacing? VUS is equal to 0.87 Fy into ASV into D by SV. So by using this formula, here I am considering the vertical stirrups. So by considering the vertical stirrups, I am going to calculate the spacing SV. So what SV will be? SV will be 0.87 Fy into ASV into D divided by VUS. So substitute all the values here. So you already calculated the ASV. Okay. So substitute the value of ASV here. What is the value of ASV? What we have calculated? ASV is 100.5 mm square. And D is nothing but the effective depth which is 400. And Fy. So Fy is how much here? For suppose I am considering the grade of the stirrups as 250. Fe 250. So Fy will be 250 here. And VUS we have already calculated here which is 3430 newtons. So substitute all the values here so that you will get the SV. So it is 0.87 into 250 into ASV is how much? 100.5 into 400 divided by 3430. So from this you will get a value of SV as 2549.1 mm. So for this shear force which has to be resisted by the shear reinforcement, the spacing what we have got is 2549.1 mm. Now let us calculate the spacing from minimum shear reinforcement. Now let us calculate the spacing from minimum shear reinforcement. What is the formula? It is ASV by D B into SV greater than or equal to 0.4 divided by 0.87 into Fy. So ASV we have already known here. How much it is? It is 100.5 divided by B also we have known, that is 300 into SV greater than or equal to 0.4 divided by 0.87 into Fy. Here what is the grade of the stirrups I am considering? It is 250. So from this you will get a value of SV. So the value of SV you will get is 182.2 mm. So this is the spacing from minimum shear reinforcement, that is 182.2 mm. Now what? Next we have to find out the spacing, the maximum spacing. So now let us find out the maximum spacing. So now let us find out the maximum allowed spacing. So the maximum spacing. How we can calculate the maximum spacing? One is 0.75D and the other one is 300 mm. So 0.75D is 0.75 into 400, which will give you 300 mm and 300 mm. So what are the previous SV values we have got? One is 182.2 mm and the other one is 2549.1 mm. So out of all this you have to consider the least value. So out of this, which one is the least value? 182.2 mm is the least value. So what we have to consider 182.2 mm as the spacing between the vertical stirrups. Now what? We have to provide 8 mm diameter two-legged stirrup spacing 182 mm center to center throughout of grade FE 250. So what? For the design, what are the stirrups I have used? I have designed for a two-legged stirrup and the dia of the stirrup is 8 mm and the spacing between each stirrup is 182 mm center to center and the grade of steel what I have used for the stirrup is FE 250, that is I have used the mild steel bars. So this is how you have to design for a RCC beam, that is we have done the design for the whole beam. We have designed the effective depth, the area of steel as well as we have designed for the shear reinforcement also.